Right, so welcome to Math 389, Operations of Order. This should be lecture 24. What I wanted to do is just do a little bit on gaps of primes. And we're gonna, for the most part, postpone finishing the gap discussion until Monday based on an absence. And I want to talk about one of my favorite math problems, egg drop mathematics. It is all it's cracked up to be. So if you're looking for something to write up for your other project, there's a chapter and then there's a math expository article. This is a great one to do. So just briefly from last time, we looked at Euclid's proof of the infinitude of primes. And it was basically, look, assume there's only finitely many primes, multiply them all together, add one. If that's prime, that's a prime that wasn't on your list. And if it's not prime, it can't be divisible by any of the primes on our list, so it has to be a new prime. So this proves that there are infinitely many primes. Wonderful. And then I don't know if we did this last time, but you could start looking at, well, what happens if we start using Euclid's construction? Well, we start with 2. 2 plus 1 is 3, which is prime. Then 2 times 3 plus 1 is 7, which is prime. 2 times 3 times 7 plus 1 is 43, which is prime. Did we talk about this last time? No. Okay. So Euclid's construction said, look, one of two things happen. You either get a new prime number directly, or you get a number that's divisible by a new prime number. So far, in all three occurrences, we have gotten the construction giving us a new prime number. Do you think it's always going to be prime? Or what would you like to do? Yeah, more data. Almost always the response is, let's get more data. Whenever you start to see a pattern, you should try to gather more data to see, is this going to hold? So when you're writing things up, it's okay to be influenced by data, but always be skeptical, always be searching to see, how hard would it be to get more data? Well, I'd have to multiply 2, 3, 7, 43, and add 1. That's not a big ask. So we can do that. And so when we do that, we actually get the next number is not prime. It's 13 times 139. I believe you can do heuristics to show that, there's probably only finitely many times that you would expect that this process would give a prime number. These numbers are growing at such an astronomically large rate. And again, if people are interested, this is a great thing to try to explore. There's a lot of questions you can ask. And so, one question is, as we go through this, which prime numbers will emerge? Will we get every prime number? We got 1, 2, we skipped 5, we got 7, we have 13 now. We've skipped, which ones have we skipped? We skipped 11. So does every prime number occur? And so you can actually construct a sequence of primes coming from the Euclid method. And this is the famous EuclidMullin sequence. And there are, two different ways of doing this. The way that's done here is you only take the smallest prime for the new primes generated by Euclid's method. What you could do is you could take all the new primes generated at a given stage and then just put them in order from increasing size. So when you look at this, 2, 3, 7, 43, 13, 53, we now get 5. The numbers get large, and then we get 11. I see 19. Does anybody see 17?
Yeah, it's on the first row.
Okay, 17 is in the first row. Good. 23. Anybody see 23? Okay, 23 is in the second row. So maybe we do get every number, but it might take a while before we get them. So a lot of these questions are still open. And again, when you're writing things, it's not bad to have some open questions. Andrew Wiles of the Fermat's last theorem fame was excited about some of this stuff by things he had read when he was a little kid. I know him, respect him greatly. I don't think he had the insights needed to prove Fermat's last theorem when he was looking at this as an elementary school kid, but it kindled the excitement. And so it's fine to put in some difficult, challenging problems and to just show that there are things that we've been looking at for thousands of years. And there's really simple questions you can ask that we just don't know the answer to. Okay. So I want to now toggle to the main part for today. I want to talk about what I'll call egg drop mathematics. So this is a really fun problem. Has anybody heard me talk about this before? Okay, so if you've heard me talk about it, then you can't suggest strategy. This is one of my favorite problems. I try to work this in whenever possible. What I love about this is there are many ways of solving it. And some approaches will give you better answers than others. And it's nice to have problems like that, where depending on how much math you know, you can get answers of different levels. Okay, so here's the problem as it was originally told to me. You have a building with n floors. We could also use what letter for the number of floors? F. But as a mathematician, I just like to use n. And we have two special golden eggs. These are extremely strange eggs. They will crack if you drop them from a certain critical floor or higher. So let's say the critical floor was 17. If you drop them from floor 17, 18, 19, whatever, they will crack from that point onward. If, however, you drop them from any floor below that, it doesn't matter how many times you drop, there is no damage done. You could drop it 1 billion times from floor 7, and there will be no damage to it. Okay? I sadly do not have such eggs in my possession, so we will consider this as a theoretical question. And it turns out that there is a lot of really good math behind this. So while I doubt any of you will be dropping eggs or things off buildings in the near future, the math behind analyzing this is extremely valuable. So the goal is to find in as few drops as possible, what is the critical floor? What is the floor from which the eggs will break? And again, whenever you're solving a problem, you want to be careful to answer the question that's asked. I will risk asking if people remember multivariable calculus. Yeah. At least, do you remember taking it at some point? Do you remember Lagrange multipliers? So in Lagrange multipliers, you want you have a constraint, some function g. You want to maximize f subject to g. And so you solve the gradient of f is parallel to the gradient of g. Grad f equals lambda grad g. And you also have the constraint g. That gives you, if you have a function of n variables, n+1 equations in n+1 unknowns. Which is the unknown you don't care about at the end of the day in Lagrange multipliers? Lambda. It's okay if you solve for lambda, but you just need lambda on the path to get to the point x1 through xn, which is the maximum or the minimum candidate. So it's a helping variable that we introduce, but at the end of the day, we don't care about its value. So when we're trying to find where is the function maximized or minimized, lambda does not matter. Over here, I don't care how many eggs we have left at the end. I just care about minimizing the number of drops. Okay. So how would you interpret finding n in as few drops as possible? I can think of several different ways to interpret this sentence. And it's amazing how often in life everybody thinks that the interpretation is obvious. And then when you ask people to be explicit, you realize that there is a disagreement. On a local issue, how many here know about the colloquial requirement for the math major? Okay, how many here do not know about it and are a math major or a stats major? Okay, so you have to give a colloquium, public talk to graduate as a math or stat major. In the old days, you could only get credits for colloquia if you went as a senior. And there was a prize for the attendance, which senior has gone to the most colloquia. And then we changed it to allow people to go up to 5 colloquia as a junior. And the question became, when you're giving the prize to the senior who's gone to the most colloquia, do you include the possible 5 that you could have gone to as a junior? How many think it's obvious? And so the department felt it was obvious. Unfortunately, half the department felt it was obvious that of course they count, and half the department, of course they don't count. It's how you interpret as a senior. Are you taking it as a senior and looking at all the colloquium they've gone to overall, in which case you can include up to 5, or just going to the colloquium as a senior? There's also great stuff about where commas are put, and sometimes this has $1 million effects in lawsuits. Anybody know what pandas do? Eats, shoots, and leaves. Has anyone heard this? So depending on how you punctuate, a panda eats, comma, shoots, and leaves. So are they eating, shoots, and leaves? Are they eating, shooting, and leaving? Depending on how you put the comma, it can make a huge difference. Given that this is a class on writing, you want to be very sure that you and the reader are on the same page. So how would you interpret finding n is in as few drops as possible? So we don't know which is the bad floor. So how should we interpret finding n in as few drops as possible? What are your thoughts? Okay, minimizing with respect to what? Okay. You need to be a little bit more explicit.
Without breaking both.
Without breaking both, still need to be a little bit more explicit. So you want to minimize the number of drops. We don't know which floor is bad. So when you talk about minimizing, are you talking about with respect to a uniform distribution on the floors, where the bad place could be? Are you talking about any prior knowledge? Are you talking about maybe protecting yourself from the worst case? Maybe I have a strategy that works really well most of the time, but really poorly once or twice. And so, if you're willing to take a chance, this strategy might give you a very small number of drops most of the time, but it could have a very high number of drops in some situations. So there's two slightly different problems. We could try to minimize the average number of drops needed. And if we do that, we need to assume some kind of distribution of which floor could it be. The other thing we can often do is we can do the worst case analysis. We can say, what is the worst possibility for our strategy for which is the floor where it will break, and see how many drops will it take in that setting. It's often a lot easier to analyze the worst case. Sometimes the average case isn't so bad. You have to analyze, of course, every single case in that situation. Can anybody give me a situation in life where you might try to minimize the worst case at the cost of some gain? Is this something that is reasonable for life? That you might have a situation where you want to protect yourself from a disaster at the cost of giving up something good? Stock trading. You might be able to make more money if you take more risks, but if you go bankrupt, that could completely destroy your personal finances. So I might be willing to settle for much smaller gain and limit my risk of having a complete calamity. You could also see this in war as well, that the danger of having the army defeated is so great that I might be a little bit more cautious. And you saw a lot of this in the Civil War, maybe a little bit too much, at times with some of the northern generals afraid to commit their forces. So for a lot of things in life, we would much rather give up a little bit of profit to protect ourselves from a bad analysis. And so I will today talk about strategies that minimize the worst case. A couple of years ago, I had a student who had a friend who put down $1,000 on the New England Patriots to go undefeated and win the Super Bowl. And this was the year they were undefeated in the regular season, won their first two playoff games, and they went to the Super Bowl against the Giants. And they were leading the Giants in the third quarter, and Vegas calls, because it's 500 to 1. If he wins, he gets $500,000. And Vegas offers to buy back the bet for $150,000. He goes, hell no, go Pats. And this is unfortunately the game with the helmet catch. Patriots end up losing. If he had been a student of mine as opposed to a friend of a student of mine, I would have flunked him. Does anybody know what he should have done? No. Not cash out immediately. Hedge his bet. He should have put a bet on the Giants. At this point, it's just one game. If he puts $50,000 on the Giants, his expected value might actually go down because the Patriots are probably going to win in that setting. But if you look at his life, If he gets $500,000 or he gets $450,000, not a big difference. Or it might have been maybe you put $100,000 on the Giants. He should have protected himself from the worst case scenario. The extra $50,000 or $100,000, the marginal utility of that was much smaller than the first $400,000. And he should have protected himself from the worst case scenario, that the amount he was playing with. Now, if he was going to be in this situation a million times, I would absolutely go with the expected value. If you're doing it that many times, things will average out. I'll play the law. But if you're only doing it once and you have to gamble, I would definitely strongly urge you in life to consider minimizing the worst possibility. All right. So general advice for life is when you are given a hard problem to do, try to do an easier problem first and build intuition. Sometimes the intuition you build from a smaller problem is not quite applicable. The problem is too easy, but it's still not a bad thing to try. So can anybody give me an easier problem to do than trying to find the critical flaw with 2 eggs? Yes.
You have unlimited number of eggs.
So is that going to be easier or harder when you now have an unlimited number of eggs? It's definitely going to make some things easy that once I lose an egg, I'm not going to be as worried. So that's one way to go, is to give yourself an unlimited number of eggs. Just having one egg. So those are the two clear extremes. I think 1 egg is going to be easier to analyze than an unlimited number of eggs. I mean, it would be wonderful to have an unlimited number of eggs. Do we actually need an unlimited number of eggs? How many do we need? N. Clearly, N will be enough, right? You might even be able to argue N minus 1 might be enough. Whenever you give a lecture in public, 0 and 1 are often the same. If I'm within 1, that's fine. I don't really want to spend the time right now and worrying about, something of size 1. Okay, so let's, don't say it out loud. Everybody think for a moment. What strategy would you do if you only have 1 egg? So you have to come up with a way to figure out which is the critical flaw where the egg will break. You don't care if you have any eggs left over once you find it, but you have to be guaranteed that you can find the flaw. Okay? And you want to do it in as few drops as possible. You only have 1 egg. So does everybody understand the problem? Right, do people want a little bit more time to think of this strategy? Or does everybody have a strategy? Everybody has a strategy? All right, somebody want to tell me, what is your strategy? Yeah, go bottom up. One at a time. There is no way we can do anything else. Nope, we have 1 egg. So what if you go every 2 floors and it breaks on floor 2?
Is the goal to find is the goal to have the egg intact?
Nope, nope. The goal is to figure out which is the first floor where it will break. So if you go every 2 floors, imagine it breaks on the 2nd floor. You don't know if it would have broken on the 1st floor.
Oh, because if it's the 2nd floor, then it breaks on the 2nd floor.
Correct.
And then you wouldn't know.
And then you wouldn't know. So if it breaks on, let's say it breaks on floor 5, you drop it on floor 2, nothing happens. You drop it on floor 4, nothing happens. You drop it on floor 6, it breaks. You don't know if it breaks because 6 was the first floor where it breaks, or 5 was the first floor where it breaks. So if you only have 1 egg, you have to go 1 at a time.
You have 2, don't you know it's 1 then?
Nope, because maybe it's okay on 1 and maybe 2 is the first one where it broke.
What if you started on 1 and went 3?
So if you start on floor 1 and then it goes to 3 and it breaks on 3, it might have broken on 2. If you skip a floor, there's no way to know if that would have been the first floor where it breaks. So if we skip any floor and it breaks at a floor above that, we don't know if the floor where it broke is the first place it would have broken. So if we go from 1 to 3 and it breaks on 3, it could have been 2 or 3. So that's the problem with just 1 egg. So worst case scenario, how many drops do we need? Is it N or is it N minus 1? It depends. If we know that it has to break on a floor and we've dropped it on N minus 1 floors, then we know we'll have to break on the next floor. And so in that case, we could get away with saying it's n not n minus 1. I don't really care about that. It's basically, it's order n. Okay? So, again, we just have to go 1, 2, 3. Worst case, it's order n drops. Okay, building on this, what should we look at now? 2 eggs. So now we have 2 eggs. Once it cracks, we're reduced to the 1 egg case. So I'll give everybody a moment or two to think of what strategy you want to do. Hit pause. I'll try to hit pause. 1. Okay, so can anybody give me a possible strategy to find the floor that's going to protect me in the worst case scenario?
This side you can go up to.
Okay, so we're going to go up every 2. Okay, another strategy.
You just go up half of the-
Go up half each time. What I love about these are extreme opposites. One of you is going halfway down, and the other one is going just a little bit. Any thoughts? Who would rather do the every 2? Okay. Who would rather do the halfway? Who's indifferent? So let's try to analyze. If you did every 2, what's the worst case? So it would take n over 2. We've got to be very careful. Plus 1, I think. So we would have to drop it on 2, on 4, on 6, on 8, all the way up to on 98. And then we have 2 floors left after that. So then this is where it gets a little bit annoying as to, do we know that if it hasn't broken for the first 99 floors, we know we get it on the next one? We could probably just do it with n over 2 and not the plus 1. But we're going to agree for today that we're not going to really worry about that plus 1. What if we do it halfway? What's the worst case for us? So if it was 100 floors, we would drop it on, say, 50. If it was,
If it doesn't turn on 50, you go to 75.
then we would go to 75. So every time you drop, you take the region you have and drop in the middle.
the second egg, you go bottom up.
Well, you have no choice. Once the first egg breaks, you have no choice. So for the second one, once the egg breaks, then we have, it's one of 2 floors. So after first egg breaks, it is one of 2 floors. Takes 1 drop. Because if it breaks on floor 6, we know it's either 5 or 6 because it didn't break on 4. And that's why it's basically n halves plus 1. Now, if we go halfway each time, what's the worst possibility for us? So when would it break? When would be the worst time for it to break? On the half floor. If we go halfway up and it breaks, that's the worst possibility because that's the most things left to do. If there's 100 floors, that gives us 50 things to check, basically. If it survives that one and then it breaks on 75, then we only have 25 things. So the nice thing about the halfway is that it's going to eliminate a lot of things very quickly. So worst case scenario here, it would be 1 from the initial drop, and then how many would we have after that? N over 2, or maybe n over 2 minus 1? Because we have 1 less floor. And so maybe that's n halves. So if there's a difference between them, it's not much. Worst if breaks on the first drop. Okay. Which do you think might have a better average runtime? the half one, I mean, the half one is eliminating so many things quickly that I might, and this would be a nice thing, if anybody's writing this up as their project, I would actually do the analysis and see what is the average runtime of the two. Given that their worst case scenarios are pretty similar, I would probably go with whichever one has a better average runtime as my final deciding factor. And if there really is a difference of one drop, and one of them has a much better average runtime, that's enough for me to take the one that has the best average runtime. Has anybody here taken advanced statistics? Okay. Sometimes there's different types of estimators you can use, and they might be unbiased estimators. And then after that, you might go to like maybe a variance minimal estimator after that. Okay, so we have two possible strategies. And then basically, you got the ones I was thinking of. Every second floor, drop it in halves. Now, of course, we could generalize, and instead of dropping every n halves, we could drop every x floors. And here, I'm going to consider this more of a generalization of dropping every second floor, where we're going to drop a fixed number of floors every time. We're going to drop x floors, then x floors, then x floors, then x floors. If I drop every x floors, what's the worst case for us in terms of the number of drops, roughly? So n over x before we finally find the first one that breaks, plus what comes after that? X minus 1. So this would be till first breaks, and that would be this. And then this would be the one egg problem. So if I do it every x floors, it's n over x plus x minus 1. Okay, and again, I might be slightly off in terms of counting by 1 or something like that. If we put in x equals 2, however, it does give us n halves plus 1, which is what we had before. So that's looking pretty good. Okay, so just writing things down explicitly, if we do it every second floor, the number of drops is n halves plus 1. If we do it n halves, it's 1 plus n halves minus 1. They're both of order n halves. And then we also had that new competing one where we drop it every x floors. And so we showed the number of drops, worst case scenario, is n over x plus x minus 1. Now, this is where the talk splits based on the audience that you're giving this to. Giving this to you all, I would do it very differently than if I was going into elementary schools, which I've done. How would you minimize n over x plus x minus 1? Take the derivative. So minimize, say f of x is n over x plus x. Why am I not dealing with the minus 1? Yeah, I mean, it's fixed. It's going to shift everything. So how do you find the minimum of something, of a function? Is that what we do? So to find a minimum, we set the derivative equal to 0. I'm sorry? All right, tell me where I'm traveling fastest, okay? The wall. Was my derivative 0 there? Now, what are you forgetting? The boundaries. Never forget the bounds. Okay? Always remember, you must check the boundaries. When I did this, I actually did break the door, which was a lot of fun. Oh, this is being recorded. But then it turns out I didn't actually break the door. I just thought I had, and no damage was done. So find critical points, check boundaries. So what's f prime of x? So now we've got to do some calculus. What's the derivative of this function? So negative n over x squared plus 1. So f prime of x equals 0 implies negative n over x squared plus 1 equals 0. So x equals n. So x is the square root of n. And what are the boundary points? So it can't be 0. 1 and n. So f of 1 is going to be n. F of n is going to be n plus 1, I think. And f of n is going to be n plus 1. And f of square root of n is basically going to be the square root of n plus the square root of n, or twice the square root of n. So where should we drop the egg? Roughly root n floors. If you think about what's going on, I'm trying to see if I have, yeah. So one way of viewing what's going on is we have two competing influences. We have n over x and we have x. We want to make this function as small as possible. How do you make n over x small? You make x big. How do you make x small? So one of the terms wants x to become small, the other wants x to become large. You can't do both simultaneously. So what you have to do is you have to somehow thread the needle, and you have to compromise. And so one way to do this without using calculus, and I'm not saying that this is going to give the optimal answer, but it might give something that's pretty close, is what if we set the two terms equal to each other? To just see roughly what would that give us, so that each term is as bad as the other or as good as the other. And so if we do that, we get n over x equals x, so n is x squared, so x is square root of n. Interesting. So the question is, will this idea always work, or is this something special with just two eggs? But by setting the two terms equal, I was able to get the sum to be what we know as the smallest, and I'm not using calculus. Now, because I'm not using calculus, I can't claim right now that this is going to be the best choice of x. I can just say this is a really good choice of x, and for this choice of x, we're getting that the number of drops is about 2 square root of n. Okay, so to try to understand things, let's assume that there's 100 floors, and let's plot how long it will take. So when you look at this, does it look like the square root of 100 is about where you should be? Yeah, it's tough to really tell small deviations. So there's actually a better way to plot this. If you look at what we have n over x plus x minus 1. We believe that x should be of size square root of n. So whenever you have some information about a quantity, you often want to try to change your variables to take that knowledge into account. So since I believe x should be of size square root of n, let me write x as t times square root of n. And the advantage is, in the previous plot, this was plotting it when n equals 100. And it's kind of tough to see maybe the n dependence as I keep changing n. But over here, when I write x as t square roots of n, when I plug that in, I get n over t square roots of n plus t square roots of n. So I can pull out a square root of n and just get 1 over t plus t. I now have a function to plot that's independent of n, and then I just rescale by multiplying by the square root of n. So I only have one function that I need to study, 1 over t plus t. And if we plot that, you can see it really does look like the minimum is happening at 1. The question is, can you prove this without calculus? And I'll leave that as a nice exercise, to see, can you prove that this function is smallest at 1 without calculus? I think it's doable. But this gives you, hopefully, a sense of how to analyze problems like this. What should we do now? So just for definiteness, I'll just leave up this slide of just writing everything up nicely. What should we do now that we've studied all this? We've done the 1 egg problem, we've done the 2 egg problem. Yeah, generalize. And before we generalize, I just want to give some advice. So imagine we have 2 algorithms. So one algorithm always takes 1,000 seconds, and one algorithm takes 1 second, except 1 in a million inputs takes a tremendous number of seconds. Is that 1 billion? Takes 1 billion seconds. So on average, both algorithms take approximately 1,000 seconds. Which algorithm would you rather use? Well, which one? The second? I mean, are you willing to gamble that only once in a million you're going to have a really bad input? That seems like a pretty good gamble. Can anybody see a good way to combine these algorithms? So the pure strategy is always do algorithm 1 or always do algorithm 2. Can somebody give me a mixed strategy? Good. So start with the second algorithm. If after a second it's not done, say screw this and go to the first algorithm. And so what you can do is you can actually get something that is phenomenally better. And we do a lot of this, in the real world, is we have algorithms that run very well most of the time, but occasionally they have bad inputs. And then we have more powerful ways to handle those bad inputs, but those methods are much slower because they have to be able to do a lot more. And so you try to do the cheap stuff as long as it works, and then when it's not working, then you switch. In some sense, this is what we're kind of doing with the egg drops. We're trying to drop as many floors as possible with a given egg, because the more floors we can leap over without it breaking, the more things we can eliminate. And then once we have the egg that breaks, then we have to go floor by floor by floor. Okay. So we can basically just, as I said, mix the two algorithms. So I don't want to go too much into this, but if you're writing up the talk today, you can actually do a little bit better than what we did. And the problem is if you always drop by the same number of floors, then the more drops it takes for the first egg to break, the worse it's going to be. You should actually do a few more floors in the beginning, because if it breaks in the beginning, then it's not so bad after you've done n over x drops. And so what you would do is do x on the first, then x minus 1 on the second, then x minus 2 on the third. So this way, the total number of drops is the same no matter when the egg breaks. And so I'm not going to go into details, but this turns out to involve the triangle numbers. And if you have n equals 105, instead of doing basically 10, you start off with 14, and it gets a little bit better. It's still going to be on the order of the square root of the number of floors. It's not going to really improve it that much. All right, so what if we have 3 eggs? So what happens as soon as 1 egg breaks? You're down to 2 eggs. And so let's say, fk of n is the worst case number of drops with k eggs and n floors. So what would f1 of n be? We have 1 egg and n floors. What would that equal? N minus 1. And so because we want to be nice to the professor at the board, we're going to just say n, and we're not going to worry about these plus 1 and minus 1s. What would f2 of n be when we have n floors and 2 eggs? Not n over 2. Where did we say what floor did we drop on if we have 2 eggs and n floors? Square root of n. So it was n over x plus x minus 1. It should be 2 square roots of n. So f2 of n would be 2 square roots of n. Right? So now let's imagine we have 3 eggs. We keep dropping the egg until it breaks, at which point it's the 2 egg problem. So with 3 eggs, the worst case scenario is how many drops do we have if we do every x? It's going to be, we do every x. So how many would it be in worst case? And n over what? X. And then how many floors do we have left at this point? Well, so now now the egg has cracked after, let's say the worst case after n over x floors. How many floors are left? I'm sorry? Not n minus x. So if we're dropping every 15 floors, and then it finally breaks, how many floors are in play? 15 or 14. But again, we're being nice to the professor, we'll say 15. So if I'm dropping every x floors, once it breaks, how many floors are left? Not x minus 3. It's x minus 1, but we're going to call that x today. So what function do I put on for the number of drops remaining when I have x floors? f2x. So this is going to be n over x plus 2 square roots of x. And we want to minimize this. So how do we minimize this? Thank you. I don't think I could do it twice in a day. I'm not going to bother checking the boundaries. We know that that's going to be fine. And so if we take the derivative, we would get f3 prime of x would be negative n over x squared plus 2. We have the 1/2 coming down. So I think it's going to be x to the minus 1/2 equals 0. So we get x to the 3/2 equals n. So x equals n to the 2/3. Does that seem reasonable to you? Are you surprised that we drop it at a greater distance than when we only had 2 eggs? No, because we can afford to have 1 egg break, and we're not in the dangerous situation of having only 1 egg remaining. It makes sense that I would try to eliminate more things. And let's calculate what is the runtime. So then f3 of n to the 2/3 would be n over n to the 2/3 plus 2. Then we would have n to the 2/3 to the 1/2. So that becomes n to the 1/3 plus 2n to the 1/3 is 3n to the 1/3. So what I care more about here is the power of n. That I'm getting an n to the 1/3. The constant 3 is nice, but that's not as important. The other way I could try to do this problem is I could say, let's let n over x equal 2x to the 1/2. Let's basically say I want those two terms to be roughly of the same size. If we do that, we then get n equals 2x to the 3/2, or x is equal to 2 to the negative 2/3, n to the 2/3. So we would still get a value of x that's of size n to the 2/3. If we just did the simpler case, avoid calculus, just set the two terms equal to each other to be of comparable size. Okay, and so let's now collect what we know. I'm going to do number of eggs, drop at worst case scenario. When there was 1 egg, we had to drop it every 1, and the worst case was n. When we have 2 eggs, we drop it every n to the 1/2, and the worst case was 2n to the 1/2. 3, we drop it at n to the 2/3, and it was 3n to the. Anybody want to conjecture on maybe what you would do for 4? Maybe n to the, we said 3/4? And what do you think the worst case scenario would be? Yeah, so the question is that, how confident are you about that 4? We have good reason to be so far. I strongly recommend you listen to the 3 blue, 1 brown, patterns fool you. This is not enough data for me to be very confident about the constant outside. However, the powers I am quite happy about. How could I rewrite any thoughts about how to rewrite the power here of n? Write that as n to what? 1 over 1. How should I write 1 over here? Almost n to the 0 over 1, then it's 1 over 2, 2 over 3. So this suggests a really nice pattern. And you can prove that you're going to get really good runtimes by avoiding calculus and just matching terms by doing something like this. Anybody know what the type of proof method would be to do this? Proof by induction. This is a great induction problem. So this is a good place to stop for today. If you want to drop any eggs, later today, let me know and I will try to provide some.